reactions of strong acids with strong bases, strong acids with weak bases, and weak acids with strong bases are the subject of this podcast, along with the corresponding plot of pH versus milliliters of titrant added. So titration curves is an interesting way to look at the change in pH as the titration progresses. More on that later on in the podcast. Right now we're going to start with the actual calculations that are involved in this kind of reaction. Since we're going to be looking at the concentrations of solutions, one way to compare is, instead of using molarity, well, we will be using molarity, but to recognize that a concentration equivalent of millimole per milliliter is another way of looking at it. So you might see that on some of these slides. Basically, when we're adding a solution to a second solution, you've got a dilution issue going on, you've got a stoichiometry problem, figuring out the excess reactant, and then calculating the pH. Eventually, you'll reach a point, which is called the equivalence point, where the stoichiometric amount of acid is equal to the stoichiometrically equivalent amount of base. And that is the point where, graphically, you have what's called a point of inflection in your titration curve. Again, more on that later. Titration reactions of a strong acid with a strong base are pretty easy, and those are the only things that are typically introduced in first-year chemistry, because there really isn't any equilibrium, since the spectator ions, the anion in the case of the acid and the cation in the case of the base are merely spectator ions. And since the acid and base are strong, you simply calculate the limiting reactant, look at the total volume of the solution, and then calculate the leftover material to figure out the pH. You've received a series of handouts from me that includes a table that's largely blank, in which the base and the acid are filled in the blanks, and you calculate the pH as a series of increasing amount of titrant is added. This example here is going to walk us through the process in an incremental fashion as well. So if we start with 0.2 molar nitric acid, 50 milliliters of it, what's the pH to begin with? Well, at the very beginning, all you have is 0.2 molar acid. So it's pretty easy to figure out the pH, since the concentration of the hydrogen ion is the same as the concentration of the acid, because it's a strong acid and it's monoprotic. So the pH is 0.699. Notice, to be consistent with sig figs, I've got 3 sig fig here, consistent with the 3 sig figs. Remember that with pH, because the number that precedes the decimal point is derived from the power of the concentration, it is only the digits after the decimal point that are used for sig figs. Now 10 milliliters of base has been added, so of course the pH is going to go up since you're adding base. Some of the base, or all of the base, will react with the acid. I think it's pretty easy to see that the amount of moles of base added will be less than the acid that's currently in the container. Now, the way that this example is set up, just to save time, is instead of converting milliliters to liters, calculating moles, and then dividing by, instead of milliliters, by liters, a step's been eliminated, so that mathematically you end up with the same process of molarity. But here you're just taking the milliliters times the molarity to get the millimoles, which is 10. You're taking the 10 milliliters times the 0.1 to get the millimoles, which is 1 millimole. They will react in a 1-to-1 ratio, producing water, but since the other products are neutral ions, there's no equilibrium involved. We have 9 moles of acid left over. Divide by the total volume now, which is 50 plus 10, 60 milliliters to get the concentration, and then correspondingly to calculate the pH. Keep in mind that as you go through this, if you had a piece of graph paper off to the side, you could be plotting on the y-axis pH, on the x-axis milliliters of titrant added. What is the titrant? That is the material that's being added to the acid. So in this case, the titrant is the base. Again, another 10 milliliters of base has been added. So now you have a total of 20 milliliters. Pause the podcast and verify that you can do this calculation on your own. At this point, 100 milliliters of base has been added. I want to call attention to something that should be pretty obvious when you look at the numbers. If you look at 50 milliliters of acid, which is 0.2 molar, and then we have double that amount, 100 milliliters of 0.1 molar, it would stand to reason that since they're both strong acids and bases, and the concentration of the base is half, that is the acid, then we're going to need double the amount of double the amount of base to neutralize the acid, which is twice as concentrated. So right now, we should be able to recognize the fact that the pH will be 7. If you look at the math, if you do the stoichiometry, you have no excess reactant. And in this case, then the only equilibrium going on is KSP. And, excuse me, not KSP, KW. And so since KW, the concentration of the hydrogen ion equals the hydroxide ion, then the pH will definitely be 7. And then beyond the equivalence point, the pH will continue to rise. Recognize at this point that what you have now in excess is the base. And so when you calculate the concentration of the ion that you're going to be calculating the concentration of will be hydroxide ion. And so when you go to calculate the pH, remember that you'll probably be calculating the pOH first and subtracting that value from 14 to get the pH. Plotting that data is what you might want to stop and do to get a ballpark idea of what was going on at this point. So this graph is very typical of a strong acid, strong base titration, where the equivalence point is at 7. Prior to the equivalence point, you have a very slow but steady rise in pH, and after the equivalence point, in that vicinity, you have a very rapid rise, and then also a steady but regular rise in pH. Now we're going to look at several other titrations. In this case, we have to do the equilibrium calculations for the next one, because what we're talking about is the reaction of a weak acid with a strong base. And so because the acid is weak, we have to first do the stoichiometry, then we have to do the equilibrium, which means that as the weak acid is neutralized by the base, you're forming a conjugate base. And so we have to do the equilibrium calculations like we've done in the past. This is exactly the same as what we were doing in the previous several podcasts, but first we have to do the stoichiometry. So you'll see a parallel, but we just have one more step, which is the stoichiometric calculations first. Again, for review, if you have a 10th molar solution of acetic acid and you start with 50 milliliters of it, yes, you have mostly acid to begin with. You have neither ions initially, and you can use the equilibrium constant, 1.8 times 10 to the minus fifth, to calculate the pH, the concentration of the hydrogen ion, and the pH at equilibrium. Next, we add 10 milliliters of base to this acid, so we have to do the stoichiometry. So we have calculations of the amount of conjugate base form, the amount of weak acid that remains, and then we can plug it in and do the calculations for pH. Finish this calculation, whether you choose to do it in millimoles or molarity, it doesn't really matter to me, but bring in your calculated pH value for this setup to class next time you have it. Remember that there are several techniques that you can use to calculate the pH. You can either use the equilibrium constant expression, or you could use the Henderson-Hasselbalch equation. Your call, your choice. Another example, now we've continued to add base. We've got 50 milliliters of the acid mixed with 25 milliliters of the base. Now let me point something out, and this is related and very important to your upcoming lab where you can calculate the pH of this situation. This is what would be called at the point of half titration. In other words, half of the acid has been neutralized by the base. And I can tell that visually by looking at the volumes because coincidentally in this case, the acid and base concentration are identical. So that means that in this case, when half of the moles of acid have been neutralized, then the moles of acid and the moles of the conjugate base are equal. And at that case, what can we say about the pH? What does it equal? Hopefully you said the pKa. Again, bring in the value that you calculate for this setup to class. And then finally, when you have 50 milliliters of base added to the acid, all of the acid has reacted. So all you have is the conjugate base. So when you're past the equivalence point, you don't have a weak acid anymore. You only have the conjugate base. This is a slightly different setup because now all you have is the conjugate base. And so what you have to do is consider the fact that this is a Kb. The acetate ion is acting as a conjugate base, reacting with water to produce acetic acid and hydroxide ion. So you'll have to go ahead and calculate Kb, which is Kw divided by Ka, in order to find the pH. Take the time, pause the podcast, to look at the slide and make sure that you understand the calculations going on here. We've taken the moles of the conjugate base formed, found the concentration, calculated the pH from the pOH, since X is the hydroxide ion. The next slide, you'll be asked to apply this in a new situation. Okay, one more example. 60 milliliters. Can you do the work? Bring that in on loose leaf as well. When you're finished, take the data from the previous few slides and the pHs that you've calculated and create a titration curve of weak acid versus strong base. The next slide I'm going to show you will be the appearance of this titration curve. So hopefully you've figured that out. My question to you is the pH at the equivalence point 7, above 7, or below 7? See if you can figure that out before the next slide. Hopefully you got it right. At the equivalence point, the pH is above 7. That's because the base is stronger than the acid. So at the equivalence point, what you have in the system is all of the acid is neutralized. So what you have when the system is neutralized is all conjugate base. And what does that conjugate base do? The conjugate base reacts with water and produces some hydroxide ions. So the concentration of the hydroxide ions are greater than the hydrogen ions. So at the equivalence point, the pH is above 7. Also notice a slight difference at the bottom of this titration curve. The pH, the slope of the pH is a little different than it was with a strong acid, strong acid, strong base titration. So down here, the pH starts a little higher, increases rather rapidly, and then levels off for a while, and then you have a steep climb. Here's a slightly more quantitative look at this titration curve. And what this slide is actually showing you is that if you look at a series of pH change at the equivalence point, you can use that if you know something about the pH at which the equivalence point will be, which indicator is a good one to choose. And you see of the two there, the more familiar, phenolphthalein. And that is typically the titration that is done in introductory chemistry, is a weak acid with a strong base. Very typical. We've used vinegar many a time in first year chem. In contrast to strong acid, strong base titration has a very different look at the initial addition of base, where it starts with a very low pH. In contrast to the weak acid, the pH was higher because there was less dissociation with the weak acid. Notice that the broad range of area, broad pH change from a very little addition of base, the pH jumps from a very low value to an extremely high value. Now, what will become important is that because of that fact, there's actually a broad range of indicators that change color over this, let's say 4 to 10 pH range. And that's why strong acid, strong base titrations are a little bit more forgiving for first year students as well. I'll show you why on the next slide. Now for your lab, you used phenolphthalein, which changes color around a pH of 8 or 9 for your standardization of sodium hydroxide. And that's a reasonably good indicator to use, number one, because of the simple color change, but also since you're titrating a weak acid, the KHP, with a strong base, the base is in the burette, then the pH at the equivalence point will be in the basic range. But if you used a strong acid and a strong base titration, really any of these indicators from methyl orange all the way down to phenolphthalein would be acceptable indicators to use for that titration because of the rapid change in pH for strong acid, strong base titrations. Conversely, this titration curve shows a strong titration, except this time what is in the burette is a strong acid and what is in the flask below it is a strong base. And when a weak base, such as ammonia, is titrated with a strong acid, notice that in this case, at the beginning of the titration, the pH does not start nearly as high. There's a gradual slope down, different than a strong base titration. Notice that the pH at the equivalence point is below 7, and then it finishes up pretty much like a strong acid would at a very low pH. And so to review, if you're titrating acids with bases, then before the equivalence point, you always do the stoichiometry, and you can use the Rice method or the ice method as we have done, or the double H or Henderson-Hasselbalch equation. At the equivalence point, since all of the acid has been used up, and beyond the equivalence point, you have to switch and use the KB, calculating KB from the Ka using Kw. Remember, Ka times Kb equals Kw. When you do that, you'll calculate the pOH, and to find the pH, you'll have to subtract that from 14. So at the equivalence point and beyond, you'll have to use Kb when calculating the pH. And of course, the reverse is the case when titrating bases with acids. This PowerPoint has a few additional details that you might want to take a look at. It also has some of the answers to the questions. You'll eventually find those posted on Edline for your use. Hope this has been a helpful podcast.